In this video, we'll be looking at the formulas that allow us to change between Cartesian coordinate systems and polar coordinate systems. So, in a Cartesian coordinate system, you're always going to have an x and a y. So, these two formulas will actually allow us to determine what x is in terms of r and theta, and what y is in terms of r and theta. This one over here allows us to determine what x and y comparatively are in terms of r, the radius. So, these three formulas are appropriately built. Now, to change a polar coordinate system, which you'll notice that, again, this could appear as though an xy system. So we're going to have to be very careful to make sure we read these questions before we actually apply them. So I have -4, 2 pi over 3, and that is the same thing as an r, theta, because it's in polar coordinates. I want to change this to be an x, y. So the easiest way to change polar coordinates to Cartesian coordinates is by simply taking the r and theta and plugging it into these first two formulas. So I'm going to have my r value, which is -4, times my cosine of 2 pi over 3, and I'll plug my values also in for y. My r is -4, and I'll have sine of 2 pi over 3. Evaluating those functions appropriately, such that 2 pi over 3 is on the unit circle. We're going to go up here and here. We know that 1, 2, and 3, this is going to be a value of radical 3 over 2, 1/2, because the x values will always decrease. So this one up here will be 1/2, radical 3 over 2. And I'm going to be in the second quadrant at 2 pi over 3, which will provide me with a value of a -1/2, radical 3 over 2. So when I plug these values in, I'm going to have a value of -4 times my cosine of 2 pi over 3 is a -1/2. And I'm going to have -4 times my sine value is going to be radical 3 over 2. This providing me with these two values negating each other, giving me a value of 2. And plugging this one in over here, I'm going to have a -2 radical 3. This is the xy coordinate plane system in terms of this point. Now this should make sense. If I were to go to 2 pi over 3, 2 pi over 3 should sit somewhere up here, and I should go to a -4, so I should sit somewhere way over here. Okay, so I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And again, this is only so I can better see the system that I'm playing with. I'm going to have this circle location, and this is going to be sitting somewhere down here. You'll notice then that if I'm going to go over 2 units and down -2/3, this is in the right general location for this coordinate to be matching up with this coordinate perfectly. The next one is we're going to convert the Cartesian coordinates to polar coordinates. So in this particular example, what we're going to do is we're going to go ahead and play with these two equations, those three equations, so that I can determine what r and what theta will end up being. So my first step is to take the x and the y and to change them into r and theta, but I'm going to start with r. The reason why I'm going to start with r is because if I take x and y and I plug that into this equation over here, I can immediately get what r is. So I'm going to have -1 squared plus -1 squared equals to r squared. This gives me 1 plus 1 equals to r squared, and therefore r is equal to plus or minus the square root of 2. So now this gives us a slight issue because it's a plus or a minus value. However, we can make note that, remember, a plus value in the radius measure is simply going to go in the direction that we want it to. A negative will go in the opposite direction. Also keep in mind that it is likely that we might find multiple different points because of the way the polar system works. The polar system can rotate around, causing us to have, say, at the value of 2 pi, a different location of the value of 0 or 4 pi. So these are my radius potential values, and we're going to come back to this value and figure out exactly which one we want. Now for our theta measures, what we're going to do is I'm going to notice that my x value has to be -1, and we have to be equal to, and I'm going to go ahead and select the positive radius measure, just because it'll be easier for us to work with. So my radius measure is going to be the radical 2 times the cosine of theta. The secondary piece that I'm going to have is my -1 must be equal to a radical 2 sine of theta. So what I'm looking at here is if I pick the radius measure of a positive radical 2, I'm going to plug both of those, so I'm going to plug radius value into both of these equations here for x and for y. I'm also going to plug in x and y, and all I'm going to be left with is a variable of theta. So I'm going to solve this like I would any other trigonometric equation. The cosine of theta is equal to negative 1 over radical 2 by dividing by 2. The cosine of theta must be equal to a negative radical 2 over 2 by rationalizing the denominator. I'm going to do the same thing with this side and get the sine of theta is equal to a negative radical 2 over 2. Now, you must simultaneously solve these two equations. In other words, what angle measure will allow cosine to equal negative radical 2 over 2, such that sine will also equal to negative radical 2 over 2. And the only location that that's going to happen is over here in the third quadrant, because this is where my x and my y are both negative, negative radical 2 over 2, comma negative radical 2 over 2. That's the point on the unit circle that will provide this to happen. And that's going to be 1, 2, 3, 4, 5 pi over 4. So the theta measure I'm looking for is 5 pi over 4, such that my radius measure is radical 2. So very carefully, I'm going to have the square root of 2, 5 pi over 4. This is one way that this can be providing an answer. You'll note that the other way I could provide an answer is such that I pick the negative radical case, and I have simply pi over 4. The reason why that is because that means I'll be in this quadrant over here with a pi over 4 angle measure, but then I'm going to go to a negative square root of 2, meaning I'm going to go, again, 180 degree rotation to this point over here. This is how, again, you very carefully convert polar coordinates to Cartesian coordinates or Cartesian coordinates to polar coordinates.